Thank you very much, Dominika, for the kind words. I should start saying that this morning I realized that I packed a combination of clothes, of nice clothes that I could not be worn. So therefore I'm a little more casual than originally planned here. But this should not conceal the fact that it's really a great pleasure and honor for me to talk about a topic which will not answer questions, I think. We're under-raced, and also not about agent-based models, but a topic that accompanied me throughout my career, started with my dissertation, computational Bayesian econometrics, and sort of came up and down again, depending on opportunities and interested PhD students, and I'm very happy that at this most exciting time in this area, I'm working with Hugo Storm, who is a collaborator you see here, and without whom the presentation you're going to see would look very different. And I'm also acknowledging the input of Kathy Bayliss to this, who always keeps me straight when I get too excited about the perspectives. So, all right, so also the uncertainty I'm talking about is not the one that face actors in our agri-food system, but rather the researcher when doing empirical analysis. So we have a time of debate on statistical practices, on statistical malpractices, not only in the agriculture economics community, but throughout, about publication bias that results from hunting significant statistical significance in the context of rather ritualized null hypothesis testing, the problems of really misinterpreting results of econometric analysis, maybe because p-values confuse or combine the uncertainty about the estimate and its size, confusion about statistical and significance and economic relevance. So there are all kinds of issues, also replication crisis, where influential papers could not be replicated when new researchers are confronted with new data, with the same data. So there's a big discussion on it, and the literature suggests all kinds of things, better training, to change reporting rules in journals, and actually some of the big journals have disallowed certain things, asterisks and so on, to move a little bit against the bad developments, but also doing mindful statistical analysis that is not ritualized and that is based really on solid theory. So that's part of the debate, relevant for the background, but also the advances that we have currently in data science and algorithms related to computer programming, which is enormous. Everybody has heard machine learning by now. It very quickly entered our curricula, and with tools that really expand the econometrician's toolbox if used appropriately. So, what do I like to get to today? Well, I want to tell you that it would be time to become a Bayesian econometrician. It's intuitive, that's not new, and it naturally embeds uncertainty, but why is it time? Because we have now new algorithms and programming languages that give rise to something that's called probabilistic programming, which allows sort of a semi-automatic Bayesian inference. It requires that the analyst explicitly formulates a data generation process, which rigorously connects theory to the inference, and allows also to flexibly include machine learning, new machine learning techniques, however, not in a pure prediction setting, but in a causal identification setting. So, Bayesian statistical inference, an intuitive treat. We summarize typically the information after an empirical analysis that we get out of this in the posterior distribution of a parameter. So that could be a regression coefficient, yeah? A parameter of interest. So the posterior distribution, it really summarizes all the information that we have, yeah, from the data, given our model assumptions and the possible prior belief. And I can interpret it, yeah, the way you see here on the right side in the slides. So there you see an interval going from -2 to +2, and then you can say, given model assumptions, the probability that the true parameter value is between -2 and +2 is equal to 95%. So if you are a classical econometrician by training and practice for a long time, then you probably kept your breath now and thought, okay, this is what we try to get rid of in our students when interpreting the confidence intervals in a frequency setting. You should never say that, yeah, what you can do here in Bayesian. So there's a much more complicated story. Here it is direct, and the posterior really has the uncertainty, yeah, and the size of the coefficient directly represented in one thing. So what is the posterior distribution? The posterior distribution is proportional to the prior information that we might have about the parameter times the likelihood function. Likelihood function we all know as frequentist practitioners as well. It is telling us, given the data, what is the likelihood to have the parameter within a certain range. So if you remember your econometrics courses, then the likelihood is mathematically identical to the sampling distribution of the data. So there you have a direct connection already between the data generation process, yeah, and the statistical inference. So there's a direct link in that likelihood here to the data generation process, and that's important for how things are going to work. Let's ignore the choice of the prior for now. There's always discussion by classical econometricians about this, or has been ideological 30 years ago. I don't want to have an ideological discussion about this. Just be aware we can always have an uninformative or ignorance prior here involved. So how can we do inference? Yeah? If we could sample from the posterior distribution that we have derived here from the equation you just saw, then we could calculate an interval or the probability that the parameter lies in an interval using integrals. Well, integrals is ugly. They can be difficult to evaluate, but what we can alternatively do is sample from the posterior if we have the chance to have a sampling algorithm. So we can just draw a sample of size n and then approximate the function really by summing across all the observations from that sample the value of that function we are interested in. So it could be posterior mean or variance, the probability to lie within a certain interval, but it could also be just the distribution itself. And what you see here in this small animation is how as more and more you sample, the posterior mean estimate gets better and the distribution gets more to a normal, which we sort of assumed here in this process. So let me say this again. If you can sample from the posterior, any desirable inference is rather straightforward. You sample enough outcomes, then you can get the function of interest as accurate as possible. Yeah. So you can also get the full distribution as accurate as possible. Well, if this always worked, then we might all be Bayesian already, but there were all kinds of problems that we had in the past. So posterior distributions don't necessarily look, or typically in real-world problems, don't look like nice normal distributions, but they can be fairly challenging. They can be difficult or even impossible to sample from. So then there are all kinds of alternative algorithms that have been developed which sort of take surrogate distributions that then are weighted or are directed in the sampling process in a way that ultimately we get some sort of outcome here that would reflect really the posterior that we're looking at. But always case-specific approaches had to be developed in the past, and the convergence of these processes could be a nightmare. The technical skill requirements are high. So, and also we have relatively limited training so far in these Bayesian methods in our typical econometrics curriculum. So, what is changing now? There's really a time of major advances in algorithms and in the programming languages. So the Markov chain Monte Carlo methods that was just already mentioned that are around for a long while, they have improved significantly, and also the stochastic variational inference that we can use to evaluate here posterior distributions, they make more and more case-specific posterior inference unnecessary. And there are also new programming languages which allow this posterior inference really to be based purely on the pure information of the data generation process without any further needs in deriving inference procedures. So this is what can be summarized, the combination of the two, new algorithms to do the inference, new programming language, which leads to probabilistic programming. So there's a literature on probabilistic programming in the last, 8 years, I would say. So the first one that introduced this to the larger community, Garamani, a computer scientist from Cambridge, said there are several reasons why probabilistic programming could prove to be revolutionary for machine intelligence and scientific modeling. First, it obviates the need to manually derive inference methods for models. And second, since it allows for rapid prototyping and testing of different models of data. Means that I'll say probabilistic programming is about doing statistics using the tools of computer science. And I want to illustrate or get this intuitively across here in the remaining minutes of my talk. So what is computer science? Computer science develop programs where they try to get most efficiently to an output given certain arguments of the functions of the programs, or here called parameters that enter the process. So statistics go sort of the other way around. We have the outputs out of a generation process in nature, in economics, whatever, where observations are observed. We develop a statistical model that would explain generation of these observations, and then we derive appropriate inference procedures in the Bayesian or classical realm to actually get the information about what is of interest to us, a certain elasticity, a certain regression coefficient, the size of a treatment effect, or whatever. So probabilistic programming is somehow in the middle here. So the way you formulate your problem is actually like computer science. You have parameters and also prior distribution on parameters. Then you write a program which is the explicit formulation of your data generation process. And then you can create with that program observations. Okay? So that summarizes what you assume about the data generation process, or makes it explicit. So when you go to inference stage, you don't need to do anything anymore. You just switch something in the program and let the program do the inference. You give the information on the observations and then let the inference machine tell you what is the knowledge in the observations and the priors, what is the knowledge in the posterior about the parameters of interest. Let's get to examples pretty quickly, but before, let me say there is an ecosystem of programming languages or frameworks that allow by now this probabilistic programming with a little bit of emphasis on Python type libraries, but is also existing in R. Hugo would argue, don't go to R, use Python, but that might be up for discussion, which I leave to him. There are new tools really on diagnosis and visualization, and there are also tools that make these procedures much quicker using graphical processing, using GPUs, just like machine learning. And here the JAX is meant, but also doing very efficient differentiation, which has not been possible before. So then these new automatic Bayesian inference algorithms, they are enormous improvements of the Markov chain Monte Carlo methods. So they are gained in speed enormously. They are also used now on GPUs or run on GPUs, and they allow larger or more complex model and sample sizes compared to the old Monte Carlo, Markov chain Monte Carlo. Then we have also stochastic variational inference, which is even much faster than MCMC, but not as accurate. So one could think about that a method that helps in model development to be quick, but then later get more accurate inference here from the new MCMC. So don't get worried. Yeah? There's computer code, and later I'm going to show some equations, but they are only there for principle. You don't need to understand the computer code to just get across the principle that we are talking about. So you have to define, and this is now done here for the linear regression. To get it into probabilistic programming, you have to define a model, yeah, the data generation process, which is pretty simple in this case. Y equal x times b plus epsilon, yeah? So everybody knows the simple linear regression. So what you do here, you define it as a function in this numpyro library. Then you define the regression coefficient, give it, as we say later, prior distribution. You define the other parameter of interest here, the variance of the errors. It also gets a prior distribution. And then, as you can see here, and then in the last line, you have a sampling statement where you sample from the outcomes y, normal outcomes y, with the mean x times b, and the error with variance sigma. So, if you don't have any data, you can just run the model, and it will do prior sampling. It can tell you something about how reasonable your model is. Does it make sense? You can test it. We will later see that. But the key thing is, once you have defined the data generation process, there's something simple you have to do to make it to an inference machine. So you see here's something said, y equal none there. Well, if you don't give the process, the model, any data, then it will do sampling based on the priors. If you give it the data on the y that you observe, it will switch the mode and actually do inference and derive the posterior distributions that exist. So, very quickly and briefly, can be easily changed to a logit model. You get rid of the sigma that you don't know, that you don't need in this context, and you change the distribution of the y, which is then not anymore normal, but a Bernoulli, or a null distribution with a logit probability link function. Okay? But let's go through some examples. The first one being a linear regression model. So here it's a simple yield prediction where the yield depends on the soil rating and the soil moisture in different months. Yeah, we took the data from our colleague Christoph Fahrmeier, who had regional average yields, n equal 148. So we use this to illustrate here some approaches. So we can do a prior sample. We use now the generative version of our probabilistic programming to test the model and the priors we have. Yeah? We use the normal prior here, normalize the variables before, and then this program samples from the prior distributions of parameters and then generates the outcome of the y's that are implied by this, and then we plot here predicted yields. So what you see here is two different priors, actually one being normal 0,1, one being normal 0,3, and these are prior yields. There's no data so far in there, but you can look what the model does given your prior distribution. Yeah? So you have on the left side between 0 and 15 tons per hectare. On the right side with the larger prior, you go into negative yields, and above 20 tons, and then you can maybe think, do I really need the right-hand side prior? Then you have recently read that the world record in wheat yield is a little less than 18 tons per hectare, so maybe you don't need the right-hand side and the smaller prior is fine. Okay, but what we can now do is we can also do a prior sampling of the regression lines that are applied without any data yet in there, and you see it can be a big mix of positive and negative across a range of constants and slopes. So we also haven't used maybe the prior information that soil rating should be have an increasing effect on yield as the soil rating gets better, but we have not included here it yet. So that's a prior, no data yet. So now you can switch the thing and expose it to data, and then we have the inference going. And what you see here in the upper line is that the data obviously give a lot of information. This very little hump you see on the bottom of that graph is the previous prior that we have looked at. But now the information concentrates really here on regression coefficients of soil rating slightly above 0, below 1. And you see that also the posterior distribution is not really much different for the wider prior here, N03. And what you see down there is then the uncertainty of the regression lines after you have exposed it to the data that you have. You see that negative regression lines are pretty much eliminated, but there's still uncertainty also depending on the ranges of the soil rating where you are that really differ. So, and the size here, the vertical distance here expresses the uncertainty that exists. Okay, let's move on and do a little bit more exciting examples to better get this understanding of how theory can be directly moved here into the program. So think about a cumulative prospect theory model. There's a game in the background. You choose between a 50-50 gamble or a payout with certainty. So you have the typical utility function with a loss aversion coefficient lambda with diminishing marginal utility here of rho, or the coefficient that can represent that. And you have a model that's the following way. These 4 equations. So if you reject the game, then you get the certain payout. So the utility of reject is the utility of the certain payout. If you accept the game, then the game is played, and you get sort of the mix between the gain and the loss as sort of the expected outcome. So then the probability to accept depends on the difference between the utility of acceptance and the utility of rejection. And you see that down there in that probability function. So that's the whole theory of the model. Forget about that it's a simple model that might not fit a lot of real situations, but this is how you would, if you use that model, describe your theory in the paper. And this is exactly how you put it in the program. So you define a utility function with the parameters, lambda, rho. There's also mu, but we set it here to one constant value, sensitivity to the difference in utilities. So, and then you have the equations that we just mentioned. You really, line for line, put them in the program because they allow you then to ultimately, after having defined prior information on the parameters, prior distributions, to ultimately sample individuals accepting or rejecting depending on the probabilities that exist. So you can generate your own sample without having seen any data if you have done that this way, reflecting your prior uncertainty on parameters. Okay, so you could now do a prior sampling as we've seen before, and then you see all possible utility functions. We had some restrictions on the theoretical plausibility of parameters, therefore some things are excluded, but there's still a lot of uncertainty given sort of the prior formulation. If you expose it to data, then you get what you see on the right side, pretty much fairly strong knowledge on where the utility function lies here, at least for that data that we used and the priors we formulated. Okay, third example, potential outcome framework, as could be more deeply read or inform yourself, Immens 2020. So heterogeneous treatment effects are of interest here, and they depend on characteristics of individuals, X. The selection into the treatment is based on the expected treatment effects. So we have equations that say, for example, the first one, expected outcome, which could be an environmental performance, it could be a profit, without being treated, is depending on characteristics and parameters alpha. The treatment effect, also depending on characteristics and parameters beta. And then we have the expected outcome with treatment, which is the sum of the, in this case, simplifying, the sum of the expected outcome without treatment plus the treatment effect. So now comes what we said, selection into treatment is based on the expected treatment effect, and that's the fourth line here, the probability to get treated is in this case a logit function that is depending on the difference between what is the outcome with treatment, what is the outcome without treatment. So then, if I have that, I can generate a population of individuals selecting themselves into the treatment or not, using the final line here, which is describing the distribution of Y, the outcomes, depending on who gets treated or not. Okay, so the principle should become clear now here. I'm not giving a lecture on the potential outcome framework, but these equations that we have just seen, those 5 equations, we can put them in now line for line into that probabilistic programming formulation. And at the end, we have then, after finding the prior distributions, at the end, then we have the sampling statement that generates data. Based on priors, if we don't give it observations, or later, using this procedure that we have defined to make inference about the parameters. So, we could also change this, have nonlinear treatment effects, straightforward to replace it here, move to nonlinear functions for the treatment effects. And the reason I'm saying this here, what is really good here is that we can also even include machine learning tools, deep neural networks, including all the training that is related to this into the probabilistic framework. So, we have here now, for this example, a cubic treatment effect, which is the true effect, that's the red line, and then we can use different types of functional forms. Obviously, linear and quadratic would have large errors. If you see here in the bottom left, cubic treatment is really good if you know the true functional form and you cannot beat it, but you can also do pretty well with a highly flexible machine learning tool here. But you use it now and you see that also the uncertainty related to that is reflected in the distribution of lines here. We could make this more ugly with a step function, sort of a threshold, then the cubic won't work well anymore, and amazing really for the main range of the data, the machine learning techniques are pretty good here. But we always knew machine learning techniques, that's why they are so prominent, are excellently predicting, but the difference here is this is now within a causal theoretical model, and we are able to depict uncertainty of that specification of the lines coming out of it. Okay, some additions on expert formulation of data generation processes. So we have use simple models to get the main points across, but there are also possibilities to have more complex individual data generating processes implemented in probabilistic programming. And there was an example here on the conference, on the Congress, that was presented by Hugo Storm, and you see sort of this graph on this here on the right-hand side that even incorporated unobservables, that could later not be filled with data, but then also observables and the outcome variables. And obviously this way you can use the system also to understand what might be causal identification issues in such a setting. So the framework allows the testing and comparison of more complex models in the development stage, even without having data. It also made us, this sort of generative model made us ourselves think about issues that we had when preparing this presentation. At some point we wanted to also include a market model, and then suddenly started thinking, okay, where do we add the uncertainty now? In the demand and supply equation, do we add it to the equilibrium? It was a matter of short and long-term horizon and so on. So, even for standard models, you suddenly start thinking what's going on. Okay, let me come to an end. So Bayesian statistical analysis offers intuitive inference directly reflecting uncertainty. This is not new. And I don't want to make it an ideological question whether you use Bayesian inference or classical inference. It has always been a pragmatic question for me. But now seems to be a time where, because of the advances, it might actually be seriously considered to move to Bayesian analysis via probabilistic programming. It helps us to explicitly formulate a generative model, which in turn helps us to really focus on the economics. Why? Because the inference step, once we have done that, is almost automatic and independent of the model of the data generation process we have formulated. So it fosters statistical inference embedded in a holistic research design process. Obviously, the theory and the inference is not all of the research design, but it is one part that has been criticized to often be not sufficiently in there and connected as well. A discrepancy between empirics and theory. Nice thing about this, we can also include new machine learning tools if functional flexibility is needed, but the good thing is they are then directly incorporated in causal frameworks, what we like to work on in econometrics. Obviously, if we want to go there, then we need updating of econometrics curricula, step by step. It's a long-run process, but I think an exciting one, and we want to start, or are about to start with that. You can find this presentation, the codes of the examples, the poster that I talked about on the GitHub link here, the QR code that's mentioned. Thank you very much for your attention.